Hello everyone, I am Fikret Garipay. Today I will present my research on bypassing PQC signature verification with fault injection, Dilithium, XMSS and Sphinx Plus. So I work as security engineer at Keysight and I'm interested in software exploitation and hardware attacks, and you can reach me on Twitter or other platforms. Today, I will start with introduction to post-quantum cryptography and how it changes the things. Then I will show how we implemented PQC target for our research. And I will also briefly introduce the voltage fault injection in practice. So even you don't have background in fault injection or PQC before, then I will cover everything necessary to understand the rest of the presentation. Then I will continue with fault injection attacks on Dilithium verification and fault injection attacks on Volts Plus in XMSS and Sphinx Plus. And I will also show the fault injection on fault resistance XMSS library, and we will wrap up with key takeaways and conclusions. So let's start with introduction to PQC. The quantum computers aren't breaking the crypto yet. They are not that powerful. However, the shift is underway. Now the standards are changing and they are forcing to PQC algorithms instead of the classic crypto. Vendors are working or they are releasing their PQC implementations, and we start to see this implementation at different devices. And PQC is going to replace the RSA and ECC in the secure boot, firmware signing, and more. So in soon, they will be in everywhere, starting your smart card up to your smartphone, which makes PQC fresh attack surface to us. And in here, you can see the four different main scheme. And Dilithium and Sphinx Plus is already standardized by the NIST. And the Dilithium is required for all digital signatures by the CNSA framework. However, the CNSA framework isn't approved Sphinx Plus for any use in national security systems. I don't know the reason. It could be the performance issues, or maybe they know attack that we don't know yet, but I'm not sure about the reason. The other two big schemes are LMS and XMSS. These schemes are still in draft at NIST. However, they are already standardized by the ISO and they are approved for firmware and software signing by CNSA framework. And as I said, now the multiple vendors are offering their PQC solutions for the firmware update, secure boot, and signature verification. For example, OpenTitan, which is open source root of trust design, also supported by the Google, is using Sphinx Plus for the PQC secure boot, and according to Google's statement, they will start to use at Chromebooks and data centers soon. And Calibra is another open source root of trust design, which is the Calibra 2.0 is adding the post-quantum secure boot with Dilithium and Kyber. So for making the attacks real, we reviewed dozens of papers and we only focus on practical attacks against the PQC signature verification. And the only problem that we started research, the public PQC targets aren't there. So to solve this problem, we ported public PQC libraries to bare metal firmware and we attacked that device. And let's check how that works. For the target implementation, we used ARM Cortex-M4 microcontroller. And for the libraries, for the Dilithium, we used PKM4, which is post-quantum cryptographic library, specially optimized for ARM Cortex-M4. And for XMSS and Sphinx Plus, these are not supported by the PKM4 yet, probably because of the performance issues. So we used their reference libraries for our research. And since these libraries are not written for the fault injection resistance, we didn't consider generic bypasses like memcompare or forced returns as threat, because we expect that secure vendors now already know how to handle these issues. So we only put our FI focus on cryptographic logic, and we only attack the cryptographic logic. So for the device, we use STM32F4. which has ARM Cortex-M4 microcontroller, and it's running a bare metal firmware, which is open source. And it has a big main loop, and in big main loop it has different cases for different algorithms, different software and different hardware implementations. For example, in here you can see the Dilithium verification case, which is receiving the signature and the message, and then rising the trigger, calling the verification function, and following the trigger. This is almost really similar to secure boot or firmware update in real world, because even we don't have triggers in the real world, we can use reset points or power traces as triggers, so it won't be a problem for us. And let's also briefly introduce the voltage fault injection in practice. So for the voltage fault injection, you have to lower the voltage at the right time to trigger the faults, and this should be not too soft or not too hard, because for example, if you set the glitch length to too narrow, or absolute glitch to too close to actual voltage input, then you will not see any change and firmware or device will just continue its normal execution, which we call normal behavior. Or if you set glitch length to too wide or absolute glitch to too low, then it becomes predictable change, which is device either going to mute or reset, which is also not interesting. However, if you can find the exact parameters between these two, you will start to see some interesting changes. And for the effects on the device, we are injecting faults to the device and then checking what's happening. And sometimes or most of the times nothing happens and devices just continue to its normal execution. And sometimes device resets, stops working or dies. This could be a bit interesting. Maybe we trigger a security mechanism and maybe this is why device stopped working, but it's usually or most of the time the mute or reset condition. However, sometimes we are seeing a change in software decision or a computational fault which can compromise the device. And for attacking all the schemes, in here you can see our fault injection setup. And we are communicating our target using UART with our computer, and to control the programmable power source and controlling the reset and the trigger, receiving the trigger from the target, we are using FPGA for the narrow timing, and all this process is monitored with an oscilloscope. And in here you can see how it looks in the real world. Okay, since we handled the basics, let's start with fault injection attacks on Dilithium verification. So the Dilithium is a lattice-based digital signature scheme designed against the quantum attacks, and it offers 3 security levels, which are Dilithium 2, 3, and 5. It supports deterministic and randomized signing. However, the randomized is selected for the standard, so this is what you are going to interface on the real world. And it optimized using entity for efficiency. And before showing the attacks, I will show the key generation, signing, and the verification process of the Dilithium to make it easier to understand the attack. And in here you can see the key generation. And key generation is starting expanding matrix A from the public seed, and then it's sampling secret vectors S1 and S2. And using the secret vectors and matrix A, it's calculating the value of the T, and is splitting this T into higher part, which is public, and lower part, which is secret. And at the end of the K generation process, the public K consists of matrix A and higher part of T, while the secret K consists of matrix A, secret vectors, and lower part of T. So difference between the public K and the secret K, we don't have the secret part in the public K. And for the signing is using a rejection loop to sample I, and then is computing the challenge C using the value of the W1 and the message hash. And then using these values is computing the Z and verifying its constraints. And the verifier doesn't know T0 because it's secret, so it creates a hint vector to help to recover the W1 at the verification. And at the end of the Dilithium signing, the Dilithium signature consists of challenge vector, Z vector, and hint vector. And the verification is pretty simple. And the verification is first computing the high bits of AZ minus C21 to the power of D, and then is correcting this result with a hint vector to recalculate the value of the W1, and using this value W1 is recalculating the challenge C from the message, and if this challenge C is the same challenge C with the signature, and if other security properties are correct, this means it's a valid signature, otherwise it's not a valid signature. And for the fault attacks on the Dilithium verification, this research is built on the fault attack sensitivity of public parameters in the Dilithium verification. And let's remember the verification line 1. And this paper shows how to recover W1 using only public inputs. And it demonstrates how to constrain the value of the C21 to the power of D, so it will minimally affect the high bits of AZ. And using these primitives, it presents two signature verification attacks to attack Dilithium verification with fault injection. And in here you can, as I said, we have two different attacks to attack the verification. And first attack is setting the value of the C21 to the power of D to 0 at the verification with fault injection. And if you can set this value to 0, then a signature generated or signed using only public key will be accepted as valid by the device. And second attack is setting the value of the C21 to the power of D smaller than the gamma 2. And if you can set this value at verification with fault injection, then a signature generated using only public key will also accept as valid. And before continue, let's check how we can generate the signatures. So paper already presents two different signature generation algorithms, and for easier implementation we modified these algorithms a little bit, and in here you can see our signature generation for the attack 1, and you can use this algorithm to easily sign your arbitrary message with public key, and then if you can set the value of the C21 to the power of D to 0 at the verification using false, then the device will accept your signature. And same for the attack 2, you can use this signature generation to sign your arbitrary message with public key, and then if you can set the value of the C21 to the power of D smaller than the gamma 2 at the verification with fault injection, then the device will also accept your signature as valid. And let's check where to target at the Dilithium verification. So we are only going to attack the calculation of the AZ minus C21 to the power of D. And to do so, we have 4 different scenarios to attack this software implementation. And first scenario is attacking downpicking of the public key. And if we can skip downpicking of the public key, then the value of the T1, all coefficients of T1 will be equal to 0. Then the value of the C21 to the power of D will be equal to 0, which enables attack 1. And for the scenario 2, we can attack the sampling of the challenge. And if we can skip the sampling of the challenge, then the all coefficients of challenge will equal to 0. Then the value of the C21 to the power of 3 will equal to 0, which also enables attack 1. And for scenario 3, we can attack the shift by D process. D is equal to 13 at the Dilithium verification, so it's shifting 13 times. If we can set this D less than 4, or if we can if we can skip this shift process completely, then the value of the C21 to the power of D will be smaller than the gamma 2, which enables attack 2. And even we cannot change anything in the calculation of the C21 to the power of D, maybe that part is secure enough, we can still attack the subtraction process to skip the subtraction of C21 to the power of D from the AZ, which is same with the setting the value to 0, which also enables attack 1. And in here you can see full attack map to Dilithium verification, at least for the software implementation. And let's check how to target. First, you have to choose your fault injection point to determine which attack that you are going to use. You can perform code review, reverse engineering, or maybe just do blindly and hope that you will hit at correct point. And then you have to generate a signature using public key and your arbitrary message using these algorithms. And after this, you can start your fault injection campaign to inject the faults at the target during the verification. And let's check the fault injection results. So in here, you can see the PKM4 Dilithium verification source code for the sampling of the challenge. And the poly challenge function is first using a for loop to override all coefficients with 0. And then it's using another for loop to actually sample and overwrite these coefficients with their actual or real values. So what we can do in here, we can inject a fault to second for loop to skip this for loop completely. And if we can do this, the coefficients of challenge will never be overwritten by the second for loop, and they will be equal to 0, which enables attack 1. And in this plot, this is a fault injection plot of sampling of the challenge scenario, and the green represents the normal execution, which device is rejected our signature, and the yellow is representing the mute reset condition, which device is either stop working or do something that not intended and not interesting, and red points are representing the success, and as you can see, we successfully bypassed the Dilithium verification using this scenario. And for the shift by D, the polyvac shift L function is using for loop to call the poly shift L function, and poly shift L function is actually shifting these coefficients. So what we can do in here, we can inject a fault to for loop to skip this for loop completely. And if we can do this, it will never call the poly shift L function, and as a result, each coefficient of T1 will remain unshifted, which enables attack 2. And as you can see, we also successfully bypassed the Dilithium verification using this scenario. And for the latest scenario, for the subtraction, we can also attack the polyvac subfunction, which is using a for loop to call poly subfunction, and poly subfunction is subtracting the CT1 to the power of T from the AZ. So as you can guess, we will attack this for loop to skip this for loop completely. And if we can do this, the subtraction is not performed, so AZ, it will only use AZ for the verification, which also enables attack 1. And as you can see, we also successfully bypassed the Dilithium verification using this scenario. So for the summary of the fault injection attacks on the Dilithium, the fault injection on Dilithium can target different verification operations like initialization, challenge generation, shifting, subtraction, or even more based on the different software or different hardware implementations. And these faults are allowing bypassing the scheme logic to accept attacker-generated signatures, which is only public key is needed to generate these signatures. And as you can see, the attack surface is pretty huge, and it will be also different attacks for different implementations, which makes fault resistance hard to generalize at Dilithium verification. So since we handled the Dilithium verification, let's continue with bypassing WOTS+ based hash-based signature verification with fault injection. So let's start with introduction to hash-based cryptography. The hash-based cryptography is built on the cryptographic hash functions rather than relying hard math problems like lattice signatures. And since quantum computers are struggling to break these secure hash functions, these schemes are remaining resistant. And at this talk, I will only focus on their fundamental block, which is also the part that I'm going to attack, the Winternitz one-time signatures, which is the fundamental block of all hash-based signatures. However, the hash-based signature is the rest of the hash-based signatures are also really complex. So we will only focus on their fundamental block. And in here, you can see a simplified WOTS tree with Winternitz parameter 4, and the hash chain length is Winternitz parameter -1, which is 3, and chunk bit size is 2. And for the signature generation, the what's first splitting message hash into message hash chunks, and then it's hashing the hash of the secret key chunk with the value of the message chunk. For example, if the value of the message chunk, hash of the message chunk is 2 at the first hash chain, then it's hashing the secret key chunk 2 times at the signing. For example, at the second hash chain, this value is 1, so it's hashing 1 times. At the third hash chain, this value is 3, so it's hashing 3 times. And at the latest hash chain, this value is 0, so it's not hashing at all, and input directly goes to the output. And this is the end of the signing process, and the vote signature is now ready. And for the verification is continuing to vote 3, where we left off at the signing. For example, at the first hash chain, since the message chunk value is 2, it's hashed 2 times at the signing. And the hash chain length is 3, so at the verification, it's hashing 1 more time, then it's reaching the public key state. And for example, at the second, it's hashed 1 time at the signing, so at the verification, it's hashing 2 more times to reaching the public key state, and then it's using a comparison function to actually calculate the actual public key. And if this public key is same with the public key stored on the device, it's a valid signature and you are good to go. However, this is not secure and we can use brute force forgery on votes. So if we can find message diggers that hash of this message is greater or equal than the original one, then you can easily forge a valid signature. For example, in here you can see the signature with 01. If we can find that message diggers with brute force search with 10 for the second hash chain, what we can do, we can easily parse the signature, hash 1 more time, since these are public hash functions like SHA-2, then to create our forged signature. And if we give this forged signature to the device will calculate the correct public key from the forged signature, and the signature is becoming valid, which is bad. So to solve this issue, we have a mechanism called votes plus, which adding a checksum at the signing, and it's also how votes is using at the all main schemes such as XMSS and Sphinx Plus. All of them is using votes plus. And this checksum mechanism is pretty simple. It's at the signing is only summing the remaining hash chains at the signing, and then it's dividing this value into checksum chunks, and it's also hashing the secret key chunk with the value of the checksum chunk. And now this is secure because, for example, in here you can see a valid signature with checksum is 6. And if we try to forge the signature with hashing 1 more time, what we are doing at the same time, we are also decreasing the checksum value to 5. However, the hash is one-way function and we don't know the checksum chunk for the previous value. And since we cannot go back, this is secure against the brute force problem. And this is the part that we are going to attack with fault injection. So for the faulting votes plus to forge hash-based signatures, this research is built on the faulting Winternitz one-time signatures to forge LMS, XMSS, or Sphinx Plus. And this paper is demonstrating an attack on the checksum calculation during the verification to decrease the checksum with fault injection. And to do so, it presents 2 different attacks, which is partial hash chain skip and full hash chain skip. And in here you can see the partial hash chain skip with forged signature that hashed 1 more time for the second hash chain, which means the checksum value should be decreased to 1 less, otherwise device will not accept the signature. And what we can do in here, we can attack false to the perform partial skip to skip one of the hash chains at the verification for the checksum chunks. And if we can do this, then the device will calculate the correct public key, and it will accept signature as valid signature. Or what we can do, for example, our brute forcer is returned message hash that we have to hash as many as the remaining hash chain at the checksum chunk. Then for the forger signature, we can perform a full hash chain skip for the checksum chunk to skip this hash chain completely at the verification. And as a result, the input for the checksum chunk directly goes to the output. And if this is your intended checksum value, then the device will calculate the correct public key and accept your signature. Or maybe we have a full hash chain skip on the device with fault injection, but we only have to hash one more time. However, with fault injection, we can skip the whole hash chain. For example, in here, we are skipping 2 hash chain. What we can do, we can easily parse the checksum chunk, hash one more time, and put there. And then, if we skip the 2 hash chain, then it's becoming our intended checksum value, which also calculates the correct public key. So what I'm trying to explain is full hash chain skip is more intended scenario for us because it's making brute forcer design easy. And for the XMSS and the Sphinx Plus, the XMSS is stateful hash-based signature scheme built on the Waltz and Merkle tree. And since it's stateful, it's requiring tracking secret index to avoid key reuse. And this is why it's recommended for the firmware or software signing, which you can keep track of index. Or what you can do, you can use the Sphinx Plus, which is stateless hash-based signature that combines forced and hypertree of XMSS instances. And with using this, it eliminates the state management. However, this comes with price that affects the size and speed. And let's check the code review of WASP Plus in the XMSS implementation. And in here, you can see the WASP public key from the signature function. And in this function, we have 2 different attack points. The first attack point is chaining length function, which is calculating the checksum value. And we can attack this function with fault injection to decrease the checksum value to our intended value. Or what we can do, we can attack the generate chain function, which is hash chain at the verification at the checksum chunk to perform partial hash chain skip or full hash chain skip. And let's check this code more. In here, you can see the chain length function, which is calling the WASP checksum function. And this WASP checksum function is computing the checksum and then is converting checksum to its own value. So what we can do in here, we can attack the checksum calculation with fault injection, or we can attack this conversion mechanism with fault injection. And then if we can set this checksum chunk value with our intended value, then the device will accept our signature. Or there's a more easy attack, which is in the generate chain function. And this for loop is first copying input to the output, the input chunk to the output, then is hashing this output at the hash chain. So it's the attack that you see on the slides. And what we can do in here, we can attack with fault injection to for loop to perform partial hash chain skip. For example, if this for loop is going to run 5 times for the checksum chunk, if we can set this to 2 or 3 to skip few of them with partial hash chain skip using fault injection, and if that's the intended value, then the device will accept our signature. Or we can inject a fault to skip this for loop completely perform the full hash chain skip. And for the Sphinx Plus, the Sphinx Plus reused the same WASP Plus code as the XMSS, and it's literally the same code at every line. So as a result, all fault injection attacks demonstrate against the XMSS is also applied to Sphinx Plus. And let's check how to target. First, you have to choose your fault injection point, and also to determine you have to perform partial hash chain skip or full hash chain skip. Then you can start brute force search for your hash biggest for your arbitrary message. For example, after injecting malicious code to the binary, or firmware, then you can start to change or add some bytes that it will not break the firmware execution or the bootloader to change the hash at every time. And then you have to check this hash that each of these hash chunks are greater or equal to original, which takes some time. And for single tree XMSS instances, it can even take up to 32 GPU years, which is attack that almost not feasible. However, for multi-tree XMSS instances and Sphinx Plus, it's doable under 1 hour with high-end GPU. And then you can start, after finding your this message digest, if you can find with your brute forcer, then you can easily forge a signature for your arbitrary message, and then you can start to inject the faults at the target during the verification. And let's check the fault injection results of XMSS. In here you can see the plot of the full hash chain skip, and as you can see, we also successfully bypassed the XMSS verification using both full hash chain skip and partial hash chain skip. So for the summary of the XMSS and Sphinx Plus, we identified multiple fault injection locations in the WASP Plus, which is used both in XMSS and Sphinx Plus. And while skipping hash chains is easy, it's easily doable with voltage fault injection. Attacking the checksum calculation and changing that checksum calculation to specific value that you will want will probably require more precise local fault injection techniques such as laser FI or EMFI. And since Sphinx Plus is reusing the same WASP Plus code, all attack techniques against the XMSS is also applied to Sphinx Plus. So let's check the bonus content, which is fault injection on fault resistance XMSS library. So far, I only attacked the public implementations which are not written for the public, for the fault injection resistance. And in real world, probably we will not be that lucky, and we will probably interface implementations that also provide some ground for at the software for fault injection resistance. And what the fault injection resistance means, it means that they are using hardened mem compares. They have different Hamming weights at the return values, and they are checking multiple things at multiple times, so you cannot bypass it with single fault or sometimes even double fault. And the Fox Crypto is released their XMSS before the fault injection attacks on WASP Plus were published. And this library is including fault injection resistance for verification at their documentation, and they are saying it's not possible to break it with single fault. They were saying that it's not possible to break with single fault injection. But as I said, this library is published before attack, so there's a way that attack can work on this library. So our goal is applying same attack to WASP Plus. And to do so, we implemented their library on our target, and we used the same voltage fault injection setup from our earlier research. And for the vulnerability, as you can, in here, you can see their chain function that hashes the hash chain at the verification. And they are checking multiple things at the multiple times, and this, for example, the value that I mark with 1 and 4 is also checked later part at the firmware. So for the partial hash chain skip, even we change the start index at the 1, then we will stuck with the assert, so we need double glitch. Or even we skip the few for loop at the checksum chunks, then this value marked with 1 and 4 will stuck somewhere later part of the code. So it's not possible to perform partial hash chain skip with single fault. However, we can still perform a full hash chain skip to skip this for loop completely. And if we can skip this for loop completely, it will create a full hash chain skip effect, and it will accept our signature. And there's no check for after this. So single fault is enough to break this library. And as you can see, we also successfully bypassed their XMSS implementation using the full hash chain skip scenario. And this is the vulnerability disclosure and timeline. Since I'm running out of time, I will skip this, and you can check after the presentation if you are interested. So let's wrap up with key takeaways and conclusions. So even the quantum safe code can be glitched, and PQC is not immune to fault injection techniques that we developed so far. It's the same processor, it's the same language, and everything is the same. And the signature forgery or generating signatures is possible without the breaking the crypto, just by skipping the checks or changing the logic with fault injection. And in future, there will be probably new fault injection attacks that no one ever think of. So even your design is secure against all known attacks that so far, maybe in the future, someone will come at fault injection attack that you never think of and can break your implementation, like in the Fox crypto case. So if you design something that you cannot update, and if hardware security important for your products, such as smart cars or smartphones, then this is bad. So that's the point that you have to consider at your design, which makes implementation security next battleground for post-quantum cryptography. Thanks for listening, and now I can answer your questions.
Thank you, Fikret. Do we have any questions? Yes, we do have a question from the center.
So I want to better understand your contributions compared to the previous work. You cited like 2023 talk for Dilithium, 2023 talk for Watts Plus. Yeah. Did they just lay out the cryptographic foundations of here's what you need to skip in order to succeed, or did they actually attack anything with fault injection? And if they didn't, then just can you say more about what you did that they didn't do?
So for my understanding, the Dilithium is sharing the code, and this is points that they are saying this is the points that you can attack. However, they are not, as my understanding, they did not perform on real device or real software implementation. And for the XMSS, they are saying that this is the points that you can attack on the diagrams, but they are not sharing that did they attack the device or not, or fault injection locations at the code that you have to skip.
Thank you. Do we have any other questions? Yes. Thank you.
My basic approach to fault injection would be to find some good settings first. And you showed a lot of slides with the graphs of length versus voltage. Why did you differentiate between those? Why did you try out multiple glitch setups? And maybe did you do some research on how this affects specific operations? So are there specific settings that work especially well for different kinds of CPU operations?
Yeah. So the device is actually that's the I want to put that on my presentation, but since the amount of the content I couldn't fit into presentation, so this is why not exists for the characterization. But my point that in this talk to show how you can attack the PQC verification on any device. For example, for different devices, you can first perform characterization to understand which locations are sensitive to skip compares or change the values of initialization, and then you can follow to generate your signature and find locations on the verification code to attack.
Perfect. Do we have any other question? We've got plenty of time. Or you want to go? Yes.
Thank you for the nice talk. So continuing on the previous question, did you look at the memory dump or something to understand if indeed that instruction was getting skipped that you wanted to target?
Before the fault injection attacks, that I simulated everything with the debugger to ensure that if I skip that instruction or if I change that instruction, it will accept my signature and it will result in the bypass. Mm-hmm. Then after the timing analysis on the verification, I was know that exact point that I was attacking, and then checking the result of the device is accepted or not.
So when you said the fault injection point, you were showing us a snapshot of the C code, but then we would you would want it at the granularity of an assembly instruction, right?
Yes, I'm attacking of course, the machine code.
Yes.
But for the for loops or the stuff that I show, it's highly chance that 99% chance that it will result in compare and test instructions at the assembly, which is really easy to attack with fault injection.
Yeah. Okay. Thank you.
You're welcome.
We have another question from here? No. All right. Last chance. Any more question? Cool. Thank you, Fikret. Let's give him a round of applause.
Thank you.